In this video, we'll discuss the problem of performing model selection with neural networks. Okay, so we've seen how to train a neural network with a specific number of hidden units, specific number of hidden layers. We saw that stochastic gradient descent could be used. In stochastic gradient descent, we have to specify a number of iterations or epochs, so the number of times we go over all the training examples and update the weights, number of times we repeat that procedure. We have to specify the learning rate, so the alpha hyperparameter that we had to specify. So a lot of these meta parameters, or we call them hyperparameters, that are required if you want to train a specific neural network. We need alpha, we need the number of iterations, we need the number of hidden units, and the number of hidden layers as well. We need also the lambda regularizer for the regularization. So how do we set these values? What's the most common procedure for performing this? So what we do typically, so this is perhaps the simplest procedure, and I'll only describe this one. You can also see other procedures for performing model selection in the machine learning literature. But the most common procedure is to take your whole data set D and split it into three subsets. It'll be a first subset, which we'll call the training set. So that could be about 70% of your data. And that's going to be used to train your model. In our case, to perform stochastic gradient descent on for a neural network. Then we're going to have perhaps 15% of the data of all of our data, which we'll put in something we call the validation set. And the validation set is going to be used to determine which hyperparameters, which values for number of iterations, alpha, number of hidden units, the regularization weight, which values for those hyperparameters are good values, correspond to a good performance on that set of data. And then finally, once we've determined the hyperparameters and we've trained a neural network with these hyperparameters that we chose as being the best hyperparameters we can find, we'll have a test set, which in this case would be the rest of our data, the 15% remaining, which is only going to be used to measure the performance of our model. So in classification, which is the main problem we're looking at here, we'd measure our classification error on the test set of the neural net we've trained with the best hyperparameters based on our validation set. So one thing that's extremely important in machine learning, that's really, really key, is that what we care about is not whether our neural net is good on the training set. What we care about is how well it generalizes to new examples. So how well does it perform on unseen examples? And that's the role of the test set. It's there to act as a collection of unseen examples that have not been used either to fit the weights of our neural net or to choose the configuration of a neural network, how many hidden units, how many layers, and to what extent we would actually train it on the training set. Okay, so this is what we care about in machine learning. We are mainly interested, so the success of a machine learning algorithm is how well it performs on a test set, on new examples. So now what we'll look at, so we've seen that stochastic gradient descent is an algorithm for training a neural network with some given hyperparameters. Now let's see how we can actually choose the hyperparameters. So what's the method we should use for searching for good values of the hyperparameters? So one of the most, so this is the problem of selecting these hyperparameters, known as model selection. Here's a few different ways of performing it. The most popular one is grid search, which I described here. So imagine, to simplify that, we have two hyperparameters. We'll have the number of hidden units in a single hidden layer neural network. So we assume just one hidden layer. And we'll have the alpha, which is the learning rate. So in grid search, what we do is that for each hyperparameter we're interested in, we're going to list a set of values we'd like to try out. So for a number of hidden units, it could be, say, 10, 100, and maybe 1,000. And for the learning rate, maybe 0.05 and 0.005. And now what we'll do is that we'll try all possible configurations or combinations of these values. We'll try 10 with 0.05, 100 with 0.05, 1000 with 0.05, and 10 with 0.005, and so on. So because we have three here, three values, and we have three values, and we have two values here, then that means that all combinations will give us 6 pairs of number of hidden units and learning rates. Learning rates. And so that's grid search. We try all these 6 values, and then we look at the resulting neural network that was trained for either 10 hidden units and 0.5 learning rate, or 100 hidden units and 0.05 learning rate, and so on. We look at all of these 6 neural nets, which one performs better on the validation set. And the one that performs better, we remember what were the hyperparameters we used, and these will be our selected hyperparameters that we'll consider as the best options. Another alternative, which works surprisingly well, is to perform something like a random search. So the idea is that instead of specifying a list, like here, a list of values for each hyperparameter, we'll specify a distribution of values we'd like to try out. So for the number of hidden units, we might be saying that, well, we'd like a uniform distribution on the set of integers from 1 to 1,000. And for the learning rate, we could have a uniform distribution, but between 1 and 0, and maybe we'll have a log uniform distribution, so a uniform distribution on the log scale of alpha, for instance. And then, so what we do here is that instead of trying all combinations, so here we have distribution. So instead, what we do is that we specify, okay, I want to try maybe 10 different configurations of the hyperparameters, and to get each configuration, I'll sample independently from these distributions. So maybe the first trial that I want to do will generate a sample for a number of hidden units of like 59, and then maybe the learning rate would be 0.0125. So that would be one trial. And then maybe another trial might be try 201 hidden units and a learning rate of 0.13. So I'll get 10 configurations like this because I specify that I had enough time to do 10 experiments. And again, what we do is that we pick the neural net with its and the hyperparameters of the neural net that performs best on the validation set as the selected hyperparameter. Again, we always use the validation set to select the best configuration, and we can always decide to actually go back and refine either our distribution if we're using random search, or the values in the grid, so in the list of values for each hyperparameter, based on the performance that we got from a first grid search or first random search. So we can always go back and forth between specifying a grid, evaluating all points on that grid, and then re-specifying a new grid, trying all the values on that grid, and trying to improve as best as possible the performance on the validation set. Okay. But the important thing is that at the very end, once we've found our best pair of hyperparameters, we now evaluate the neural network with these hyperparameters on the test set, and that's the performance of that we can expect from that neural net on new examples, because the test set was not used either to train the neural net or to choose these values of hyperparameters. Finally, if for the number of epochs, or sometimes I'll say number of training iterations, so that's the number of times we loop over all training examples. So for the number of epochs, instead of saying, okay, well, I'll try 10 iterations and then run a simulation and see what's the performance of the validation set, and then I'll say, okay, well, maybe I'll try 100 iterations instead, and so on. So train from scratch a neural network with 100 iterations. What we can do instead is to actually track the validation set error as training progresses. And what we'll typically do, if we also track the training error, what we typically see is a curve like this. We'll see that the training error will always get better and better and better. That's because we're more or less directly optimizing the training error by doing stochastic gradient descent, so we expect it to always decrease. However, the validation set error will start being better and better, and then eventually will become higher. Actually, the real thing that's happening is that the gap between the training and the validation set error is expected to always increase. And so for that reason, at one point, the training error won't decrease enough for the validation set to also decrease. It'll start increasing in absolute terms. And so what we want to find is the number of epochs here that corresponds to the best validation set error. And so what we can do is that we maybe train the neural network for one iteration, and maybe that's the performance. And then for one more iteration, we start from that neural net and do one more iteration. So we get these values here. And then do one more iteration and get these values. And once we reach here, we'll see that now the validation set has increased. So that's an indication that we're starting to overfit. And so because there might be some variation across iterations, it could go back down a little bit. And so for that reason, instead of stopping right away, often we use something I call a look ahead. So we'll instead allow for training a few more iterations, and once say I'll use a look ahead of 5, once the validation set error has not improved for 5 iterations, then I'll just stop and I'll go back to the neural net that had the best validation set error. So I'll remember that I'll maybe save the weights of my neural net for that number of iterations. And that's the procedure known as early stopping, and that's the procedure that we often use to specifically for determining the number of training epochs or training iterations for the neural network. All right, and I should say that this curve here, we expect to find this curve not just for the number of epochs, but also for the number of hidden units. So if we train a neural net with, say, 10 hidden units, and then we train another neural net with 20 hidden units, another one with 30, one with 40, and so on, we also expect that the gap between the training and validation set error is going to increase. And so if we have a neural net that's too small, that is, it could be made bigger and we'd obtain a better validation set error, we say that we're underfitting. And if it's the other way around, if now our neural net that we're trying is actually too big and we should decrease its size, we'll say it's overfitting. So it's essentially starting to learn by heart what's in the valid training set, and that's not helping it, and that's actually hurting it in terms of how it performs on examples that it hasn't seen, the examples in the validation set. And just in general here, this label could be replaced by any hyperparameter that increases capacity. So the more capacity I give to my neural network, the more the gap between the training set and validation set error is going to increase. All right, so that covers the different notions for doing model selection. We can use grid search or randomized search to select the number of hidden units and the learning rates and so on. And for the number of iterations, we can actually use early stopping. So given the number of hidden units and say a learning rate, I can use early stopping for these two hyperparameters to select what's the right number of iterations for that number of hidden units and that learning rate. All right, so that covers model selection.